Hello and welcome to the electron configuration notes. The first couple slides that we're going to go through will reference back to what we talked about with quantum numbers, and having a good understanding of quantum numbers makes writing out the electron configuration easier for you. So again, going back to the quantum numbers, our first quantum number was N, corresponds to the energy level that that electron is in, and essentially we had said it was the row that the element was in. The transition and intertransition metals were off slightly. Then we have our sublevels, which was our SPDF sublevels. Then we had our orbitals. So again, we found our number of orbitals by doing the negative end of L to 0 to positive L, and that corresponded to the number of orbitals those electrons could occupy. And our fourth quantum number was the spin. Each orbital can hold 2 electrons, and one will be a positive spin and one will be a negative spin. So we have our 4 quantum numbers here: N energy level, L sublevel, again that's our SPDF, M sub L our number of orbitals, and then M sub S our spin. So when considering the electron configuration and quantum numbers, there are a couple rules we need to keep in mind. The first one is the off-ball principle that states that electrons are always filled in from the lowest energy level up, the lowest energy level being that 1 energy level, or that first energy level where hydrogen and helium are. The second rule is Hund's rule that says when you fill in the electrons into the orbitals, you have to half fill the electrons with the positive spin in one positive spin electron in each orbital first, and then you can go back and pair them up with a negative spin electron. And then the third rule is a Pauli exclusion principle that says that no 2 electrons can have the same 4 quantum numbers. So this is where your notes pick up. There are 2 different ways that we can write out the electron configuration. One is known as the SPDF notation, and the next one, which is on the next slide, is known as the orbital box notation. So the SPDF corresponds to obviously that second quantum number, SPDF. This is an example for hydrogen, which has an atomic number of 1. So we always start off writing the energy level. So hydrogen is in the first row of the periodic table, first energy level. It's in the S sublevel, and it's the first one over in that row. So this is going to correspond to the number of electrons in that energy sublevel. So the electron configuration for hydrogen would be 1s1. The second way is again that orbital box notation. So we're going to move on to helium now. So the SBDF notation, again, helium is in that first row, that first energy level, in the S sublevel, and it's the second one over. So 1s2. And showing it with the orbital box notation, again, we would write the energy sublevel right below the box, and then we have our first electron in, which corresponds to hydrogen. And then if you look down here in the green, these are hydrogen's 4 quantum numbers. First energy level, the S sublevel in the 0 orbital, and it's the first one in with the positive spin. And the second arrow in corresponds to that second electron in that 1s sublevel, which is helium. And this red arrow corresponds to the red 4 quantum numbers down below. This shows you the order that the electrons fill, always starting with the lowest energy level and then moving to higher energy levels. You might want to add in this little zigzag on your paper. It is very helpful to figure out what energy sublevel comes next. So again, we always talk about the off-ball principle, lowest energy level first. So we fill in the 1s, so it'd be 1s2. Then we move on to the next row down, 2s, and it would be 2s2 when that's filled. And then we move right on from left to right across the periodic table. Next is the 2p. Next row down, 3s. Move right across the periodic table, 3p, then 4s. And then our transition metals are off actually by 1. So after 4s comes 3d, 4p, 5s. And then after 5s, our 4d, the second row in our transition metals, 5p, 6s. And then this again gets a little tricky because after 6s, that comes in our first row of our inner transition metals. And then the third row of our transition metals, and then 6p, 7s, then our second row of our intertransition metals, and then 6d, 7p, 8s. This is another way of showing it. Again, essentially that zigzag is just moving left to right and down, left to right and down, left to right and down. So 1s2, 2s2, 2p6, 3s2, 3p6, and the 2 and the 6, because there's 2 elements in that S. In all p sublevels, there's a total of 6 elements. After 4s, this first rows are 3d because there's 10 elements in that d sublevel. So 3d, 4p, 5s, 4d, 5p, 6s, and again, this is where the first row of our intertransition metals is inserted into our periodic table. So 6s, 4f, 5d, 6p, and then 7s, and then here comes our 5f, 14, because there are 14 elements in that F sublevel, and then 6d. So again, it's just left to right, down, left to right, and down. So this is the orbital box notation for calcium. They're not boxes, they're circles, but same exact thing. So that first electron in is for hydrogen and then helium. I'm going to use red. And then we move down to the next one. So we have lithium and then beryllium. And now left to right, now it comes our 2p sublevel. So we have boron, carbon, nitrogen, 1 electron in each of the orbitals, the positive spin in first, and then you go back and you half fill. So then we have oxygen, fluorine, neon. When that is filled, you go to the next higher energy level. So now we have sodium and magnesium. Left to right, now we're at aluminum, silicon, phosphorus, and then we're at sulfur, chlorine, argon. Now our 3p6 is filled, and then we move to our 4s. And again, calcium is in our 4s sublevel, the second one over, so that first electron in corresponds to potassium, that second electron in corresponds to calcium. If you add up the total number of arrows, it should total the atomic number for that particular element if you did it correctly. So if you added up all these arrows, it should be 20. If we write out the electron configuration in the SPDF notation for calcium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So again, if you added up all of these exponents, it should total 20 if you did it correctly. Before moving on to the next slide, I would like you to pause the video and turn to the next page. I have 6 examples for you to try to write out the electron configuration using the SPDF notation. So pause it. It's helpful to have a periodic table in front of you. Try it out yourself and then come back to the video and you can check your work with mine. All right, welcome back. So our first example was carbon. So I locate carbon on the periodic table. It is number 6. And it's in the 2p sublevel. It's the second one over, so I have to end at 2p2. So always starting with the lowest energy level first. Oops, didn't mean to do that. So I start at 1s2, that takes care of hydrogen and helium. Then 2s2, lithium, beryllium. And then second one over in our 2p sublevel, 2p2. Adding up the exponents, 2 plus 2 plus 2 is 6, which corresponds to carbon's atomic number. The next one is oxygen. So again, we're in the 2p sublevel, the fourth one over, starting lowest energy level first, 1s2, 2s2, 2p4. 2 plus 2 plus 4 is 8, which corresponds with oxygen's atomic number. Next one is sodium. It is in the third energy level, the S sublevel, and it's the first one. So it's 3s1 where we have to end, but we have to fill the previous sublevels first. So 1s2, 2s2, 2p6, 3s1. Adding up those exponents will total 11, which is sodium's atomic number. Next example is neon. Neon is in the second energy level, the p sublevel, and the sixth one over. So 1s2, 2s2, 2p6. And we say if you wrote out the orbital box notation, which I will show you right here. So we have, I'm going to just show them horizontal, 1s, 2s, 2p, because there's 3 orbitals for p sublevels. So we have hydrogen, helium, lithium, beryllium, and then we have boron, carbon, nitrogen, oxygen, fluorine, and neon. So all the orbitals are filled, and when that happens, they are very, very stable, and that's what you will find with every single noble gas. They're the outer energy level, which is our 2-second energy level, every single orbital is completely filled, which makes it very stable. To the next one, we have bromine, which is number 35 on the periodic table. It is in the 4th row down in the p sublevel, the 5th one over, so I know I have to end at 4p5. But all the previous sublevels and energy levels have to be filled first. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and again, we can't forget after 4s comes that first row of the transition metals, 3d10, and again, because there's 10 elements in that row. And then we go left again, going left to right, 4p5 comes next, and it's the 5th one over. And again, adding up all the exponents will total the atomic number for that element if you did it correctly. Now, the longest one of all is gold, number 79 on the periodic table. It is in the 5th energy level in the D sublevel, and it's the 9th one over. So starting lowest energy level going to highest one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, first row of our transition metals, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now again, this is where our first row of our inner transition metals comes in, 4f14, and then following again left to right, 5d comes next, 5d9. Adding up all of the exponents should total number 79 on the periodic table. This slide isn't in your notes, but it's showing you the orbital box notation for oxygen and then also the SPDF notation. And it's color coded, so the green goes with the green, the yellow goes with the yellow. So again, 1s2, 2s2, 2p4. So again, half filling each orbital first with that positive spin electron, and then once they're half filled, you can go in and half fill it in with that negative spin. Sometimes you'll see the orbital box notations written horizontal, or you might see them stacked up on top of each other. This next example of chlorine, we're going to do both. We're going to kind of combine this, doing the orbital box notation and the SPDF notation all in kind of one example here. So chlorine, I locate chlorine on the periodic table. It is number 17. It's in the 3rd energy level, the P sublevel, the 5th one over. So I'm going to start 1s2. So that's hydrogen, helium, down to the next energy level. So that's my 2s2, that corresponds to lithium and beryllium. Left to right, 2p6, we half fill them, boron, carbon, nitrogen, oxygen, fluorine, neon. Next row down, 2s2, first electron in corresponds with sodium, then magnesium, and then going across, we have 3p5, aluminum, silicon, phosphorus, sulfur, chlorine. So if I added up the arrows, it should total 17. If I add up the exponents, it should total 17. In the next 3 examples, given the orbital box notation, trying to figure out what element corresponds to each diagram. A very helpful hint is essentially you just need to look at that last one. So if you know the locations of the energy sublevels on the periodic table, it makes it really, really easy. So I look at 3p2. So I look 3p, third row down in the P sublevel, the second one over is silicon. Another way of looking at that is you can add up all of the arrows. And again, those number of arrows corresponds to the number of electrons, and then it should total 14 on the periodic table. Looking at the next one, 2p5, second row down, the P sublevel, and that is fluorine. And totaling the number of arrows, 2, 4, 6, 8, 9, and number 9 on the periodic table is fluorine. In our last example, we look here, 3s2, third energy or row down, second one over, and that is magnesium. Adding up the number of arrows, 2, 4, 6, 8, 10, 12. Magnesium's number 12 on the periodic table. So now we're going to look at an abbreviated method to write out the electron configurations. If you think back to that gold example, it took us a pretty long time to write out the whole electron configuration for gold. With the abbreviated electron configuration, or you might hear me call it the noble gas electron configuration, it condenses it and makes it a lot easier for us to write. So group 18, the last column in the periodic table, are known as the noble gases. And in the previous example, a couple slides back, we wrote out the electron configuration for one of the noble gases, and I had mentioned that that they were stable and they have a full outer energy shell, and it makes it convenient for noble gases because they are at the end of each row. So instead of always starting with 1s and continuing on, we basically just find our element and find the noble gas that comes right before it, and then continue on writing the electron configuration as normal. So for example, if we're looking at sulfur, sulfur is number 16. The noble gas that comes right before that is neon. So I'd start with neon and then continue on as normal. If I'm looking at tin, number 50 on the periodic table, the noble gas that comes right before that is krypton. So I'd start with krypton and then write it out as normal. So we are going to write the abbreviated or noble gas configuration for zinc. So we first find zinc on the periodic table. It's number 30. It is in the third energy level, the D sublevel, the 10th one over, so 3d10. I've looked back and find the noble gas that comes right before it, which is argon. And then I just continue on as always. So I start with argon, and then I go down to the next row, which is 4s, so 4s2, and then 3d10. I always like to check my work, so I like to write the atomic number for the noble gases up as an exponent, so I can add up those exponents, and it should add up to the atomic number for that element if I did it correctly. Next, we're going to look at the unabbreviated configuration and also the abbreviated configuration for sulfur. So sulfur is number 16 on the periodic table, so it has 16 electrons. Unabbreviated, 1s2, 2s2, 2p6, and then 3s2, 3p4. You can see here I talk about core electrons and then outer core electrons. So the core electrons are the ones that are closest to the nucleus. Outer core electrons, if you pay attention to that first quantum number, it's the ones that is the farthest from the nucleus. It has the highest number. So there are total of 6 electrons in the outer shell. So we've got 2 in the S sublevel and 4 in the P sublevel. The core electrons are taken care of with that noble gas. So that these 10 are just taken care of by writing neon, and then you continue on and write out just the outer electrons after the noble gas. On the next slide, I have a couple examples for you to try on your own. We have oxygen, magnesium, and cadmium. So pause the video, try to write out the abbreviated method for those 3, and then come back to the video and check your work with mine. So looking here, oxygen, I find oxygen on the periodic table. It's number 8. The noble gas that comes right before that is helium. So helium has 2 electrons to that. So then I go down to the next row, which is the second row. So I start out with 2s2, 2p4. For magnesium, magnesium's number 12 on the periodic table. The noble gas that comes right before that is neon. Neon has 10 electrons. And so then I go right down after that. And so I have 3s2, 10 plus 2 is 12. Cadmium is in the 4D sublevel. The noble gas that comes right before that is krypton, having 36 electrons. So then you go down to the next row, start out with 5s2, 4d10. So you don't always start with one s like we did with the unabbreviated method, but after you write out that noble gas, you will always start out with an S because it's the next one that comes right after the noble gas. Back in Unit 1, we had talked about atoms, and again, those are atoms that have either lost or gained electrons. If you lost electrons, you become more positive, and if you gain electrons, you become more negative. So we'll take that into consideration when writing out these electron configurations for ions. We also have something on the periodic table we call the main group elements. They want to have the same number of electrons as the closest noble gas, so they will either lose or gain electrons to become like a noble gas. The main group elements are columns 1 and 2, that S sublevel, and then the last 6 columns of the periodic table, that P sublevel. So it's the tallest columns on the periodic table are also known as the main group elements. So when writing out the electron configuration for ions, we're going to do the exact same rules, but we will then just take into account whether the ion has lost or gained electrons. My clue or hint to students that are struggling or did struggle with ions is to write out the original electron configuration first and then go back and consider that charge, whether it gained or lost electrons, and then you can adjust that last electron configuration. So for example, sodium. Sodium is number 11 on the periodic table. It is usually ends at 3s1. So if we wrote it out, we'd have 1s2, 2s2, 2p6, and normally writing it out with the neutral atom, it would be 3s1. But that negative one tells me it lost one electron, and it's going to lose the electron that is farthest from the nucleus, which is this one in the 3s sublevel. So we lose that last electron, and then we have an electron configuration like a noble gas, which is neon. We move on to nitrogen with a -3 charge. So if writing it out as normal, we would have 1s2, 2s2, 2p3, but this -3 tells me it gains 3 electrons, so I add 3 electrons to that last exponent, which was 2p3, and I ended with 2p6. So again, it has a full outer energy level, has the electron configuration as neon. It's happy, it's stable. Next is oxygen. Oxygen, 2p4. The closest noble gas is neon, so it's going to try to become like neon. So writing it out as normal would be 1s2, 2s2, and then normally it would be 2p4. This -2 tells me it gains 2 electrons, so I add 2 to that 4 and I get 6. So these are known as isoelectronic because they have the same number of electrons as a noble gas. In this case, that noble gas is neon. So that only kind of happens with those main elements on the periodic table. The transition and intertransition metals are slightly different, and you'll see that with this next example of iron. So iron is in our 3D sublevel, the 6th one over. So normally we would end 3D6, but this +3 tells me that it loses 3 electrons. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and normally it would end 3d6, but it loses 3 electrons, so we end 3d3. And that is the end of our notes.